The next big topic about uh, neural networks is the loss function. So as we have seen, the weights are chosen to minimize the loss function that you choose. And the loss function, what we will see now are different options that we have, but typically what you have is a combination of these options. So uh, there are two kind of problems: regression problems and classification problems. So in the regression problems, you are trying to predict a y, so an output that is a continuous number. So you could have something like the mean mean bias error. So it is just the difference between the two, and this is a seldom used in training. And then you have the absolute average bias. So absolute average bias is this one, in which the difference is in absolute value, and it is also called the L1 norms, or squared distance, that is L2 norm, or the square root mean square error, that is this one, with a square root. Then you have the Hoover loss. The Hoover loss saturates. So the problem with the absolute, with the average square error, is that if you are close to the minimum, it goes very quickly, much quicker than the absolute value. So the absolute error is I don't see which one it is. This one. So it is this one. But the square error goes faster if you are close to the minimum. But the problem with this is that beyond a point you are giving an excessive importance to having large errors, while this one is not. So somehow the Hoover error is being just a square error if your error is smaller than delta, and then a linear function if it is larger than delta. So below delta it behaves quadratically, beyond delta it behaves linearly. So you don't give so much weight, and you are not so much dominated by incorrect input data, outliers of your examples, and so on. And then here you have this log cosine, hyperbolic cosine, this function. So it is somehow similar to the Hoover loss, but it's non-parametric. So in the Hoover loss you have to choose the delta. Here you don't have to compute the delta, but because you are using logarithms and hyperbolic cosines, it is more expensive to compute. So those are for regression problems. For classification problems, we have to encode our data in some way that can be easily handled mathematically. So let's say that we have two variables like gender or location that take multiple labels. So the one-hot encoding, we create new variables, gender male, gender female, location south, location north, and so on. And then they take value 1 if your input data has that label. So male, this guy is male from the south, so it will have gender male 1, gender female 0, location south 1, and all the others 0. So these indicator variables, they take value 1 if you have that label, otherwise they take value 0. So that is why it is called one hot, because if you look at all the locations for a single entry, you have only one, and here you have only one, here only one, here only one, there all the others are always 0. So this is called one-hot encoding. So once you have your data in one-hot encoding, then your y will be either 0 or 1, and then you can compute these kind of losses. So these kind of losses are, for instance, the binary cross entropy. So the binary cross entropy is y, remember it is 0 or 1. This px of I, pxi, xi is your input, so it is the individual that you're trying to classify. Pxi, it is the probability predicted by the network to belong to class 1. So let's say that you predict, so you have to predict a 1, and you do predict a 1. So this is 1, this is 1, and logarithm of 1 is 0. So 0 times 1 is 0. So there is no loss on this side. You have 1 minus of yi, that is, but yi is 1, so this part doesn't count. And if you study all other combinations, then you have this penalization that if you have to predict 1 and I don't predict 1, I will get a loss different from 0. So in general, this prediction coming from the network will look something like this. So let's say that we have to predict for 3 different locations, for instance, 1, 0, 0. Then our prediction is 0.7, 0.2, 0.1. So we are more confident that it is coming from the first location, but not from the other two. But still, these two we would like to go to 0. This one we would like to go to 1. And then the calculation is this one. So these labels here will be using these weights, and this logarithm here, they will be using the labels. So this is the cross entropy. So the cross entropy is this one. So it has almost the same flavor as this one. And the binary cross entropy somehow is a particularization in which you know that the other class, if one is 0, the other one is 1. So this is a particular case of this one. Then we have other possibilities, like these hinge laws. So these hinge laws somehow penalizes the wrong and the right but less confident predictions. So f of x, depending on how strong your prediction is, so if your prediction is 1 or 0.9, 1 is stronger than 0.9 and 0.9 is stronger than 0.55. So somehow this takes that idea that if you want to predict 1, be strong about your prediction. So it penalizes wrong predictions, which is good, but also right predictions, but that are not very confident. So this is the hinge laws, the KL laws, the Kullback-Leibler laws, that is defined this way. So here is our prediction, and this is what we have to predict. Somehow they all have the same idea. So if you have to predict 1, 0, 0, the network should be penalized for not doing 1, 0, 0. If you are doing image processing, and in particular image segmentation is this problem in which you are given an image, and then you have to assign labels to each one of the pixels. So you have multiple labels, and then you have to assign those labels to those pictures. Then, as we said, the loss functions, typically they can be a combination of losses. So for instance, we can have kind of local and global information during the optimization. So the local information is about the pixels themselves. So we have somehow to assign classes to each one of the pixels. So this is a manual process. You have to label all pixels here. And then you compare the predictions for the class C. The class is wall, floor, bed, table, curtain. So these classes play the same role as these. As this one hot encoding variables. Okay, so this is just the standard cross entropy. So for multiple classes, so you have the segmentation information, but then you can add semantic information on top. So for instance, now we can construct new variables to decide, for instance, YC takes the value 1 if the class C is present in the image. So let's say that class C is a curtain. So is a curtain visible in this image? Is the curtain visible in this image? Is the pillow visible in this image? Yes or no? So for the different classes that you can have a global loss function that somehow is attached to the class. This one is attached to the pixels. So this one is attached to the whole image. And so it is a kind of similar to what we did before, but now for each one of the classes you have a binary cross entropy, and this loss function is local, this loss function is global. This is called semantic encoding, and then you have a mixture of those two loss functions, and you can add as many loss functions as you would like, always making sense in your particular context. Here are more segmentation losses for images. So this cross entropy we have seen. Dice loss is defined this way. Pi is the predicted probability of being inside class 1, and Jacquard is so all different variations on a combination that somehow penalizes predictions that are wrong with respect to the label. If you make divisions, you have to be particularly careful with dividing by 0, so that is why you always have to this epsilon, and then this epsilon is also added to the numerator just to keep the loss consistent, so that if you make a perfect prediction, the loss function is 0. There are a different set of losses that are also very interesting. These losses for ranks. So let's say that you now, instead of having one input, one output, what you have is 3 different inputs. So you have 3 different inputs that you will call anchor, negative example, and positive example. So positive examples, so for instance, I want to classify if an image, so I want to put all the images of dogs together and all the images of cats together, but not to mix dogs and cats. So in anchor, I take one image at random. Let's say this is a dog. Then the positive will be another dog in a different picture, and the negative will be a cat. So what I want is that after learning the latent representation of the anchor dog is closer to the latent representation of the positive dog, and those two are closer than the anchor and the negative, that is a cat. So somehow, if you think of the anchor here, so what you want is that after the learning, all the cats are here, well separated from your dog, and then all that you have surrounding are dogs. And maybe there is a cat that looks like a dog, and then that is a hard negative. If it really looks like a dog, that will be a hard negative. It will be very difficult to the network to make a representation of that cat such that it is far from the representation of a dog. And then you have a region called semi-hard negatives. So it looks like a dog, but not so much. And you define this margin. So the margin is one of the parameters that typically all these losses have. So how far you want the representation of a dog and a cat to be, so that they are not mapped onto the same point. So if the distance is larger than this margin, then you assume, okay, you did a good job. so I will not penalize it. I will not penalize you. So we have presented here three different losses. One is contrastive, triplet loss, and margin ranking. So the description I have made is more similar to the triplet loss. So the triplet loss, you have the distance of the positive, so anchor positive, the distance of anchor negative, so, and then if it is larger than a margin, you don't want to penalize too much. So if this is larger, if this subtraction is larger than margin, you don't penalize. And well, don't penalize would be this one, max and max. Okay, so if the here it is the distance between a pair of embeddings. So here the embeddings, if it is a positive example, yi will take value 1, and if it is a negative example, it will take value 0. So if it is a negative example, if it is a positive example, you want to minimize this thing, and if it is a negative example, you want to minimize this one. So if it is negative, this one is 0, this one is 1, and then if your distance is larger than m, the maximum will act, and then there will not be any penalization. And yeah, and this one is the same. So this is margin ranking score, so margin ranking loss. So you are scoring your sample to belong to the positive class or not. So you take the score of a positive example, the score of the negative example. So you're given the three, but you are scoring this one and scoring this one to say if they are similar to the anchor. And then your score will be between 0 and n, not n, it is unbounded. And then you have a margin, and then this maximum somehow makes this idea that if your negative score is larger than the margin, then there is no penalization. More rank losses. This one is acting on the latent space, so this information noise contrastive loss. So you have the representation of the anchor, the representation of the positive, the representation of the negative. So these are the latent representations of your input points, and then you need a function to compare any representation to the representation of the anchor. So this can be dot product, cosine similarity, whatever, and you have one positive and then many negatives. So what you compute is the average. So the expected value is the average of how the positive looks with respect to the anchor, and then for all the many negatives, how they look to the anchor. So what you want is to minimize this loss. Let's say that you are generating images. So if you are generating images, there are these generative networks that create new images, new data, whatever. So what you have is this possibility. So for instance, perceptual loss. So perceptual loss, you have the generated image that you just generated and a true image. And then for each one of these layers we already saw what they are tensors, so this tensor of values. So if you have the tensor of values corresponding to any one of the nth layer, so if you have the tensor associated to the generated image and the tensor associated to the true image, these two should be small, because what you want is that the generated looks like the true images. And typically you do this with pre-trained networks. So you take any network that works on images, for instance, to classify what kind of data you have on what kind of images, cats, dogs, I don't know, birds, whatever you have in your picture. So you take this VGG network that is already trained to do that task, but now you wanted to use it as a perceptual loss. So a perceptual loss, the network stays fixed. So it is a different network, the one you're optimizing for your image generation. And then what you do is that your network is producing a generated image. You pass the generated image through the VGG network, and you pass the input image through the VGG network. And what you ask is that these two look similar, and you can do that in this way with Euclidean distance, or you can also do it in terms of distribution. So the distribution of these numbers should be similar to the distribution of these numbers, and so on. And also, for instance, you want your images to be smooth. So your images to be smooth, you can penalize with the total variation. So total variation is computing the difference between one pixel and the one on the right, and one pixel and the one below. And so these are these two. And then you want these differences to be small, and that is promoting smoothness. This total variation is known that, for instance, if you have noisy observations of a 1D signal and you minimize something related to the total variation of your reconstruction, then your reconstruction tends to be relatively flat within those areas. Another application losses that is specific to some particular problem is this image style transfer problems. So the image style is you have this image, you have this picture, and you want to transfer this style of this picture to this one, and then to get something like this. So what is the kind of losses that you can use there? So for that, what you can do is for every layer in your network, you can compute it's called the gram matrix, and you want the gram matrix of your generated image to be similar to the gram matrix of your style image. So this is the gram matrix, the definition of the gram matrix. So if you have a set of vectors, that is what we have in each one of the layers, we have some tensors. So if you put those tensors as vectors, you compute, and that is the matrix A, compute A transpose A. So what you want is that A transpose A for your predicted, for your generated image, is similar to the A transpose A for the style image for each one of the layers of the network. If you have some text, so in this text, so you have multiple losses that can also be used, and some of the most common, so if you think of each one of the words as a class, as a one-hot encoding class, as we did before, one possible loss is that the network has to predict the next token. So you have in a sentence, you have a number of words, so you have to predict what is the next word in the sentence. This is one this is one possibility. So for instance, let's say that 1, 2, so all of these have class numbers. So this is class 3198, 11, 734, so on. So after this one, what is the next word? So the next word is 3 with probability 39, and with probability 16, 2 with this probability, and so on. So then you so these large language models, what they do is to take somehow, not necessarily the one with maximum probability, but one of the ones with maximum probability. And you can do that for the next word, but you can also do it for any word in the middle. So for instance, you have a sentence, and then what you have is how are today doing. So what is the word that is here? So it is the same kind of problem, but not the next word, but any word that I have maxed out from the sentence. And this is somehow the basis of some famous models before these, now LLMs, that was BERT. And the idea is we can extend that to the next idea prediction, not predicting the next token, but predicting the next idea. Then you have sentences, so you have to predict the whole sentence. That is the next idea. So these large concept models, they do that. So Tim wasn't very athletic. So what is the next sentence? He thought that would change if he joined the sport. And this is a natural explanation. Or because he was not very athletic, Tim could not join the teams to improve. And then the next sentence, the next idea, concept, so he decided to train on his own. So this idea of predicting the next thing, we can put it with tokens, we can put it with sentences, which is a very powerful idea. So here you have some links about loss functions, and that will be it for the loss functions.